A vector space is a generalization of the spaces R to the n that we were talking about before, like a generalization of the R2 space or the R3 space. So the familiar Rn spaces are going to be vector spaces, but are not going to be the only ones. So vector space will generalize that idea. And a vector space is going to be actually any non-empty set. I mean, can be any set, not just the set of vectors that we have been seeing before. Any set. With any set, I mean any set, the set B could be the set of chairs in a room, for instance. So it can be any set. So, and this set is going to have to be equipped with two operations. So, the element of this any set, if this set is a vector space, are going to be called vectors. So this is going to be the name of the element. So if the space is a vector space, its elements are going to be called vectors, but are not going to be necessarily the familiar vectors in R3 or R2. So any elements that this set has, if the set is a vector space, are going to be vectors. So for instance, if our set is a set of chairs, so each chair is going to be called a vector. So each of the chairs will be each of the vectors in the space. So in that way, when we talk about vector addition, this is not going to be necessarily the addition of vectors, the regular vectors in R3. No, this is going to be any operation that we invent in the space and that we call vector addition. I mean, we take one chair and another chair and associate the addition of these two chairs. That should be a new chair. So that is as inventing goes. So we can invent an operation that we call addition and another operation that we call scalar multiplication. In the particular example of R3 or R2 are going to be the addition, the regular addition of vectors and the regular scalar multiplication. But in general, in all the other cases, no, because the elements are just not vectors. So we need to have then a non-empty space and two operations. These operations have to satisfy, though, these 10 axioms here. So these 10 axioms go like the first two, that what are called the closure axioms. What they said is that if we take two vectors, and I remind again that vectors don't mean the regular vectors, means any elements in the set. If we take two elements in the set, then the addition of them should still be in the same set. And if we take one element in the set and one number, the scalar multiplication of them should still be in the same set. Once that we prove that the two operations satisfy the closure axioms, I mean that when we do the addition and when we do the scalar multiplication, in both cases the result remains inside of the set. That's why they are called closure. So after we have the operations defined like that, we also have to check that they satisfy also the remaining 8 axioms. These axioms are like regular properties that the operations with vectors do satisfy, but so any other space that we are trying to see if it's a vector space should satisfy those. Should satisfy that the addition is commutative, that the addition also is associative. So if we had to add 3 things, it's the same that if we add first these 2 and then the third, or if we add these 2 and then the third. Also should have the existence of something that acts as the zero vector, meaning that some vector that when we add to any one remains the same vector. So some vector that added to any other keep the vector as it was. And also should be satisfied the existence of additive inverses, meaning that the addition the invented addition, should have this property that should exist a vector in the space such that added to a particular vector we obtain the vector 0, the vector that acts as a 0. And also these distributive properties, I mean, if we do the scalar multiplication, should be equal to these two. And if we do addition of numbers, so that's why it's a scalar addition, just addition of numbers. So if we add these two numbers, should be the same that if we do the addition here. This is addition of vectors. This is addition of numbers. So be sure that in each of the properties you check what kind of objects you have at each step. And finally, should be the scalar multiplication should be associative. So if we have to multiply a vector by two numbers, this is just a multiplication of numbers. So should be the same that if you do the scalar multiplication here and the scalar multiplication here. You see that there are different types of multiplications, right? So here is multiplication of numbers. Here, both times is multiplication, scalar multiplication, the one defined for this vector space. And finally, the last property, the property 10, says that when we multiply by just the number 1, a vector, I mean the scalar multiplication, we should obtain the same vector. What do we need to do to check that some set, right, I mean any non-empty set, is a vector space? Well, first we have to identify the elements in the set, like the chairs that I was talking about before. So those elements are what we are going to be calling vectors. So then, once that we identify the elements in the set, we need to identify two operations, the addition of vectors, I mean the addition of elements, whatever these elements are in your particular set, and the scalar multiplication. So once that you identify the two operations in this particular set, then you have to check the two closure axioms that we saw at the beginning, and then check all the other 8 axioms. So, for instance, let's start with this set. The set F is going to be the set of F such that F is a function from R to R, meaning the familiar functions, right? The functions F that you know from the R to R, right? So these kind of functions. So let's check if this is a vector space or not. Well, first we need to check, as we said before, identify what are going to be the vectors in this case. Well, this is a set that has functions, right? I mean, all the elements in this set are functions. So the vectors are going to be then the functions. So each of these functions is going to have the name vector. Okay, because the elements of the set, any elements, are going to be called vectors. In this case, the elements are functions. What? Well, the functions are going to be our vectors. And then we need to identify what's going to be the addition and what's going to be the scalar multiplication. Well, so if we have two functions, f and the function g, these are going to be just two generic elements in this set, right? Two functions, I mean, two vectors. So how am I going to add these two vectors? I mean, how am I going to add these two functions? Well, I have to invent an operation that takes two functions and returns another function. Well, I can just consider the regular addition of functions. So I can consider that the addition of this is going to be the function h obtained as f of x plus g of x. So, meaning that a new function h at each value of x. What is going to be the value of h of x? Well, the addition of these two. So if this one, the green one, is equal, let's say, to 2, and this one is equal to 3, well, then h of x is going to be equal to 5. that's going to be our function. And whatever, so but for each x we calculated, and this is going to be the addition. So the addition, then we identify the addition. We can just take like the regular addition of functions, and in the same way we can define the scalar multiplication. I mean, a number k multiplied by a function, we can define it by just doing k times, I mean this times will be the timing numbers multiplied by the value of f of x. This is our function f, how we define something multiplied by f, for instance 3 multiplied by f. Well, we just for each f of x we multiply the value by k. So for instance the function 3f will be a new function such that for each value x is this 1. When we multiply it by 3, we'll get the value 3. So that's going to be the value of our new functions. And so with all of them, we do like that. So we will get something like this. That will be the function 3f. So we have then two operations well defined for functions, the addition of functions and the functions multiplied by a number. So we identify then addition and scalar multiplication. And now we need to check the closure axioms. That means that if we take two functions, when we add them, still we get a function. I mean, we still get something in f, right? And in f are just functions. That happens, right? The addition of two functions is a function, and the multiplication by a number is still a function. So we got that the closure axioms are satisfied. I mean, I don't go outside of the set. So when I multiply or when I add, I get something that is still in f, right? That is still a function. And then the remaining will be to prove all the other axioms. That will mean that to prove that the addition of functions is associative, etc. And that in this case is true. So we can say then that because of that, f is a vector space. Okay, and this is our first vector space that is very different from the Rn or R3, right? So this is a vector space whose elements, whose vectors are functions. We are going to be doing operations with functions. Okay, another example, let's consider the space of matrices. So this is a space that is familiar to you, right? So you know what are the matrices of dimensions m by n. So this is the space that now is going to be our candidate to be a vector space. First, we identify the elements of this space. Well, the elements are going to be matrices. So our vectors are going to be matrices now. So the ones that are going to act as vectors are going to be then the matrices. So do we have an addition? Do we have a multiplication by a scalar? Well, just the regular addition of matrices and regular multiplication by a scalar of matrix will actually satisfy all the properties. So the addition will be the regular addition of matrices, and this will be the regular multiplication by a number. And let's check if these operations, the regular operation in matrices, really satisfy, for instance, closure. That would be an interesting one that not always will be satisfied. Let's see if for these matrices, m by n is satisfied. So what do we need to check? We need to check if this matrix is a matrix m by n, and this one is m by n, so the addition is really a matrix that is m by n. Well, the answer is yes, right? So then it's still in the same set. So the addition has closure, keeps inside of the same set. And if we multiply a matrix by a number, so that also belongs to the same set, right? Because if this matrix was m by n, when you multiply by a number, it's still m by n. So the closure properties, the closure axioms are satisfied. And you can check that all the other 8 axioms are also satisfied. Let's see now something that is going to be very useful, and is checking, once that we know what a vector space is, now we can say we have already examples of vector space, right? The Rn that that we have seen before is a vector space. The space of the functions is a vector space. The space of the matrix n by n is also a vector space. So now, once that we have examples of vector spaces, we are going to be interested in knowing if subsets of them are also going to be vector spaces. So we are going to define, this is a new definition. This is the definition of subspace. So if we have a subset, you see the difference between subset and subspace, right? A subset is just anything that is inside of another set, but a subspace is going to be a subset that satisfies some extra conditions, that has a structure on it. So, and a subspace is going to be then a subset of the space that is a vector space itself under the addition and scalar multiplication of the big vector space. So, with this definition, we will have to prove all the conditions, right? To prove that something is a subset, because the definition is simple, that is a vector space. So we will need to prove the big definition of vector space. But this theorem gives us a shortcut. This theorem says that actually to prove that something is a subspace, we only have to prove that it's non-empty and that the closure axioms are true. These are the only ones that we have to prove, because the remaining 8 axioms, just because this is inside of something that we knew already that is a vector space, is going to be inherited, the other axioms. So, to prove that something is a vector space, we have to prove simple that the operations remain in the subset. So that if we take 2 vectors that are in the subset, the addition is still in the subset, doesn't go out. And the same thing with the multiplication. For example, considering the space R2, a familiar space of vectors that we know. So let's consider a subset of it. So for instance, let's consider this subset here, this part. This is going to be our W. So now, the question is a subspace? And so for that, we have to check that if we take 2 vectors in W, so then the addition is still in W. So let's check that. So if I take, for instance, this vector that is in W and this other vector that is in W, you can see that the addition, by doing the parallelogram here, is actually outside of the space. So that means that we took 2 vectors that they were in W, but the addition is not in W. So what means is that W is not a subspace of R2. So we prove that W is not a subspace. Because already the addition is not close in the space. We could see also that the same also fails for the scalar multiplication, right? Suppose that you have, for instance, this vector here. When you do the scalar multiplication, let's multiply by 2, for instance, we get this, or by 3, we get something like this that is outside of W. So, in order to be a subspace, so when we do the operations, should keep everything in the space. So let's see this other example, still in R2. So let's suppose that now our W, our space, is this line. That's W. So the question is the same. If I take 2 vectors in W, does the addition still is in W? So let's check. If we take this vector, for instance, this vector U, and this vector V, well, when we do the addition, in this case, the parallelogram is very thin, right? Because both vectors are in the same direction. So the addition of these two, it is really in the same direction. I mean, u plus v. I mean, it's going to be still in the same line w. And we can see also that, I mean, this part is true, but we can see also that it's also true for the scalar multiplication. I mean, any vector that we take in this line, for instance, this vector here, this vector u here, when we do the multiplication by scalar, we obtain something that is still inside of W. So this property is also true. So this line W is going to be a vector subspace. So W is then a subspace of R2. So this line is a subspace, but see that depends on the position of this line, right? I mean, if we have instead a line, let's say, like this, that's going to be different. So let's call it this line T is actually not going to be a subspace. So if we think here of two vectors in T, so it should be that the extreme of the vector is in T, right? Like this one and this one. Observe that any addition here will go outside of the line. Same thing with the multiplication. I mean, a vector like this, when we multiply by something, gets outside of T. So T is not a subspace of R2 then. In the same way, we can see that in R3, if we consider a plane, for instance, like this, I mean, this plane here, this is a subset of R3, but it's not going to be a subspace because of the same reason, right? We get one vector here, one vector here. When we do the addition, this vector goes outside of the plane. Though, if we get a plane that actually passes through the origin, so let's see, for instance, this plane that we can see here. So the plane determined by the axes x and z. So this plane here, this is going to be a subspace. So that is, we take a vector here and another vector here. When we do the addition of these two, the addition here, it is going to be still in the same plane. So all the planes that pass through the origin are going to be subspaces. Or all the lines that pass through the origin also in R3 are going to be also subspaces. Okay, so this is going to be one of the most important examples of subspace, and it's going to be a subspace of the set F. I mean, the set of all the functions. Well, inside the set of all the functions can be anything, right? Like an exponential, a sine or cosine, a parabola, any function that will be elements in the space of functions. But if all the possible functions, we consider only the polynomios, the polynomios is going to be contained in the set of functions, right? I mean, we are not going to consider the sine or cosine or the exponential. These are not polynomios, but for instance, the parabola is a polynomial. So it's going to be a subset of all the possible functions. The polynomios is a subset of them. Let's consider, for instance, specifically the polynomials of degree 3, let's say. So let's imagine that this is the set that this is a subset. The polynomials of degree 3 is in particular a subset of all the functions. Let's see if this is going to be a subspace. So the polynomials of degree 3, let's imagine this one. This is a polynomial of degree 3. We add it to another polynomial of degree 3. So what do you think? Is the addition going to be a polynomial of degree 3? Well, not always. Imagine that we have x cubed plus 1, that's one of the polynomials, and the other one is minus x cubed plus 1. So we add these two polynomials, x cubed minus x cubed cancel, 1 plus 1 is 2. So this is not a polynomial of degree 3. So because of this happened, the polynomial went down, right? Because some degrees cancel. So that means that if we add two polynomials that have exactly degree 3, So the resulting is not going to be a polynomial in the same set. I mean, it's not going to be a polynomial of degree 3 necessarily. So that means that the polynomials that have exactly degree 3 is not a subspace. But if we modify a little bit this set, let's consider now what is called P3. P3 is the set of polynomials such that the degree of P is less or equal than 3. So this set that is still a subset of F, right? P3 is contained in F. This one is going to be a subspace, and it's going to be an important subspace. The polynomials that have degree less or equal than 3. Imagine that now I take a polynomial that have degree less or equal than 3, and I add to a polynomial that have degree less or equal than 3. The resulting polynomial still will be a polynomial that have degree less or equal than 3. So that means that the addition has closure. And the multiplication by a number also. So if we multiply k by a polynomial, so the polynomial, if this polynomial was degree less or equal than 3, the resulting polynomial will still have degree less or equal than 3. So polynomials in general, Pn, will be the set of polynomials of degree less or equal than n, and this space is going to be always a vector space.